Thank you, Stelio. Good afternoon. I am Nikos Bakas from GRNet, and I will present parallel computing techniques for scaling hyperparameter tuning of gradient boosted trees and deep learning. Initially, we will start with the statement of the problem when scaling the hyperparameter tuning of machine learning models and the corresponding computational bottlenecks. We will use for this work XGBoost. I will present some results from Luxina supercomputer. We will discuss a bit about the CPU threads and processes and the parallelization strategy we follow. Then we will propose a cross-validation algorithm for the case of hyperparameter tuning, because it affects the tuning, the accuracy, and the compute time, and also the search space of the optimization algorithm, where we search for parameters, for the optimal parameters. Then I will present how the parallelization is performed using multiprocessing, the Python package library multiprocessing. Also some problems we had and how we resolved them regarding multiple OpenMP runtimes. And finally, some scaling up results. Okay, the idea is that we want to optimize the machine usage. I have a comment. Please turn on the sound. You don't hear me? People online, can you please confirm that you hear me? Or okay, thank you. Okay, thank you very much. Perhaps it's a problem with Goran. Goran, if you could check your... Okay, thank you. Okay. So Goran, probably it's a problem with the settings of the sounds on your machine. Okay, also I would like to say here that I prefer to be this an interactive session, so please feel free to interrupt me, ask anything that is not clear, and everything. Okay, the idea is that, of course, we want to create the best possible machine learning model for our problem, and also we want to optimize machines' usage. I mean, now modern supercomputers on the CPU partition usually have 128 or 256 threads. We don't want the threads to sleep. We want to utilize them as much as possible. We will focus on tabular datasets, and particularly not very big datasets necessarily. This is, despite many works exist for deep learning and tuning machine learning models on GPUs, we will now focus on the CPU's usage. The reason for this is twofold. First of all, if we have a large GPU and a small dataset, usually the training on this GPU is slower than on a small GPU, because we have the problem of communicating the threads, etc. So, or also, if we use only 2 gigabytes, let's say, of a GPU, and the GPU is 32 gigabytes, it is meaningless. And also, of course, other works exist for this. I will focus on CPUs, how we can utilize a big CPU on one node, but to utilize it optimally and to solve this problem of hyperparameter tuning, because despite the size of the dataset, the problem still is computationally very demanding. So we need to find the best possible model, especially, as I said, in industrial datasets where we have a lot of noise. We need to find a model that generalizes well, and even 2 or 3 or 5% of increase in the accuracy can be very important in practical cases. On this particular CPU of Meluxina, we have 256 threads on each node. And the idea is to send one model for it to be trained on each thread or per few threads. I will explain this in detail. In this slide, we can see the scaling of XGBoost on this CPU with 256 threads without any modification, the plain package. We can see that if we have small data sets like 10,000 samples and or even 100,000 samples, but up to 10 or 100 features, columns in the dataset, parameters, then after the 10 threads, the scaling is almost 0. And also, the pattern of the scaling is not very, the slope of the scaling curve is not very big. We have scalings of 4 if we have 10 threads, for example, so, or a scaling of 2. So we cannot claim that XGBoost scales really well on this on big CPUs. However, if we have many features, many parameters, then it scales really well. This is probably because the parallelization for XGBoost regards the training of each, the selection of each node of the tree, which is an iterative procedure and can be processed in parallel. So if we have many features, it scales well. But, however, usually we don't have like square datasets. We have tall matrices with many samples and few features, and we will focus on that. Okay, the architecture of Meluxina is this. We have the compute node containing 573 nodes with 2 AMD of 64 cores each. And similarly, the GPU partition, which is really big and is not very useful for our problem. Okay, a few reminders regarding cores and threads. We have the CPU, which is the main processor, and this is divided into many cores. Now, each core can have multiple threads. So the idea is to use the threads. Because of hyper-threading technology, we can utilize multiple threads per core. In our work, we will use some threads, 1, 2, 3, 4, usually up to 10 because of this graph here, because after 10 threads, the method does not scale, which might be on separate cores. And the idea is to run them in parallel, distribute the models in parallel. How we do this? We send computationally, I mean, send one model on each thread. This is the simplest case. We send one model to be trained on each thread. However, if we have, let's say, 100 models to train, different models, 100 not epochs or iterations, 100 different models to train, and we have 256 threads, then we distribute the threads accordingly. Some models will run on 2 threads, some on 3, and some on 1. And then we leave the package to do the parallelization. We leave XGBoost and OpenMP to do the parallelization. Now, regarding the cross validation strategy, as I said, we have data sets with a lot amount of noise, with a big amount of noise. So we need, during training, to assess the generalization capability of the model. Usually, we split the training set to a validation set and let's say sub-training set. And this is performed randomly. This is not very good because if we think a bit on this, some of the samples will overlap with the previous split, because we do this for many folds. We do not split once, we split for 5 or for 10 folds. So when training, we will utilize some samples many times, and perhaps some samples not at all, by randomly splitting the train and the validation set. Here we follow another strategy. We split, we randomly permute the samples such that they do not overlap. Usually, I use 5 folds and 20% for the validation set. However, this is parametric. I will provide you also with the computer code. Now it is only the presentation because it is a bit complex, and I would like to clarify things, but I will provide you also with so if we follow this strategy, if you see here the yellow samples, none of them overlap among them. They are all distinct. Okay, this is a schematic representation, but if we do the same for a big data set, we have the same image. So regarding tuning, the first thing we suggest is doing this, following this cross-validation strategy. The second is that during training, let's say I am training a deep learning model, and I have the loss function for the train and the validation sets. If I do hyperparameter tuning in deep learning, I fix the number of epochs. I tell the algorithm, search for 100 epochs, then search for 200, 300, etc. However, we miss here a very useful information regarding the optimal number of epochs within the maximum number of epochs I trained this particular model. So if I train for 100 epochs, actually I have information regarding 100 models, each model with different number of epochs. So the second idea is this, that we track all the number of epochs per model, and we select only the optimal. The third idea is here, is this. We split the tuning process, because I guess we all know that this is a very heavy computational process. We split this process into two distinct regions. Initially, we train a lot of models, let's say 1,000 models here or 10,000 models, because in order to reach robust results, we need to train a big amount of models in order to have statistical significance of the results of the tuning. So at the first stage, we train many models, like 1,000 or more, but for a few number of epochs, because usually if the information, whether the model overfits or not, is obvious, is apparent in the few epochs. For example, in the first 100 epochs, we will know if the model overfits. Similarly, for XGBoost, in the first 100 rounds, we will know if the model has a good accuracy or not, generalization accuracy, cross-validation accuracy. Afterwards, we have the second round, which is inversed. We have a big number of epochs and few models. So from the initial 1,000 models, we select the best 100 models, and we train all of them for many epochs now, in order to investigate the full potential of this particular model architecture. One parameter we have to set is the final blast threads, how many threads we will need for our final model, because after the second round, then we select the final model. But we selected this by using cross-validation, so by not exploiting all the training samples. So we need to train again, the final model. And in order to do this, because we have really many threads, we keep only 10 or 20 final threads. Okay, regarding the tuning parameters in the search space of the optimization algorithm. For XGBoost, we optimize these parameters. The first is the maximum depth. This is the depth, the maximum depth of the tree. If we use high values for the depth, then we have the model is more prone to overfitting. If we use few values of the maximum depth, then the model is slow. We will need more iterations. So, which is the optimal number, we don't know. We check a range from 1 up to 10 for this parameter, for the maximum depth. Then we have the learning rate, the ETA, as it is called in XGBoost. Similarly, with the maximum depth, when we have low values of learning rate, the model generalizes well. When we have bigger values, then the model is faster, but might result overfitting. So here we search a space from 10 to the minus 3 up to 10 to the minus 2, a linear space with 3 samples, another 3 samples here, and 5 samples in the domain 0.1 up to 1. Then we have the column sample by tree, how many, the percentage of the columns that will be randomly sampled for each tree, which again helps generalization. This is a wider domain. We use values from 0.1 up to 1. The same for subsample, which is the fraction of the samples to be randomly selected. And then we create all the possible combinations among those parameters. If we do the calculations, if I remember well, this results to 10,000 models. Although I did not select a very small step, for example, for the learning rate, the resulting search space of the parameters is quite big. I mean, if I have 10,000 combinations, then I need to train 10,000 models. So this is a bit computationally, okay, not a bit, it is very computationally demanding. I have a comment regarding the Python code. Of course, I will send you the code and everything. After the seminar, I will send it to Stelios to send it to you. Okay, so somewhere here closes the XGBoost. Now, let's go to the tuning parameters for the artificial neural networks. As we said, I will use PyTorch, a very well-known library for deep learning. And regarding the tuning, we will tune these parameters. First of all, the number of layers. How many layers we will use. We can never know. I mean, even from theory, we know that neural networks can approximate any analytic function, any continuous function. However, we don't know the best possible network architecture. So especially for the number of layers, which is very affecting the number of layers affects the computational time because then the weights increases exponentially with the number of layers. If I double the layers, then I have an exponential decrease in the weights because of all the interactions among them. So we select here a range from 1 up to 10. Of course, we can change this. We can select more layers up to 100 or this depends on the problem, or the particular problem we have. But usually, this is a good start. Then similarly for the number of neurons, we select a range from 1 to 10, and then from 20 to 100 with step 10. The learning rate, we start from 10 to the minus 4 up to 0.1, 3 linear spaces among them. Then we use the dropout. We also use dropout because this is very helpful for noisy data sets with values ranging from 0.001 up to 0.5. The batch size, usually we use a range from 8 to 256. Here I start with a 2 to the power of this range. This is a very big number. And then I bound the batch size such that the maximum of this is the observations over 4, the size of the 1/4 of the size of the dataset. We also use momentum that helps the algorithm to avoid the flat regions and the local minima in this range, and we get all the combinations. Now let's see how many are these combinations. Out of curiosity, in order to have a better image of the problem. And of course, I underline that this is not an exhaustive search. This is only a number of layers. Here we have 2 million combinations, 2.5 million combinations. If we combine all the possible parameters, then we have 2.5 million combinations of parameters. So that means that we need to, if we do grid search, for example, we need to check out 2 million models. Okay. So this is impossible, especially for deep learning, because we will need like some thousands of years or more to train a simple model. I will now present how we avoid this, the exhaustive search. If you train a machine learning model with hyperparameter tuning and keep track of the tuning of the accuracy of each model during tuning. And then if you plot the results, here at the left figure, I have trained 10,000 models randomly. Let's say I have 2 million combinations. I randomly select, totally randomly, the first 10,000 models. And I present the 5,000, the half of these models. I plot the train, validation, and test accuracy. Then I will have an image like this. If we see this, first of all, we can see that we have an overfitting, but because this is XGBoost, we could say that we do not care a lot, because even though the training accuracy is higher than the testing, the validation and the testing accuracy are almost identical. You see, we cannot even see the validation curve here. It is under the green curve, the test curve. Okay. The first observation is this. The second observation is that if we see this from a statistical point of view, personally, I used to assess statistically the process of selecting a model, because when I have a good accuracy, if I don't assess this statistically, then I cannot claim that this accuracy did not happen by chance. So I have to assess the tuning process. Now, if we see this curve, it is almost a straight line, so the distribution of the accuracies in the validation and test set are uniform. We have a uniform distribution. This for the first round at the left figure. At the right figure, for the final 100 models, for the final, for the second round, as we said, we have two rounds. The first is a lot of models and a few iterations, and the second round is fewer models, the best models of the previous round, but with a lot of iterations, a lot of rounds. So at the right figure, the 100 final models have again a uniform distribution, and the range among the best model and the worst model of the final models is really narrow. We can see that the range is from 0.998 up to 0.9995. Okay, it is after the third decimal point. So we can claim, why I am presenting, we can claim that the process is convergent. Although I am not exhaustively searching for the entire search space, because we have to train for 2 million models. If I train only for 10,000 models, then the process is convergent, and the final increase in accuracy has a very few chances to be significant. Okay, so by using this strategy, we can have a robust tuning algorithm. I say again, before we proceed with the multiprocessing part, I say again how we do the tuning. First, we select a good cross-validation strategy. It is important that the faults do not overlap among them. Secondly, we do not only keep the final epoch result for each model during the tuning. We keep track of all the epochs. This way, we have a lot of models to check which is the best. I mean, for each epoch, we have a different model. Then we split the tuning process into two rounds. The first round is few epochs and many models. The second round is the best models of the first round, the best, a small fraction, the 10% or the 1%, but with many epochs. And of course, the final train for the final model. We select an appropriate space for the search parameters, and we see that this process is convergent. I will now proceed to the multiprocessing part, but if you have any questions, please feel free to ask before we continue with the multiprocessing. Write in the chat, whatever. Either everything is clear or, okay. How can we apply these methods to models that, okay, yes. This is not very useful for models that take weeks to train. However, I have to say a couple of things here. If we have a model that takes weeks to train, the most probable is that we have a lot of training samples. We have a big data set. When we have a big data set, then tuning is not so important like when we have fewer samples to train. Because if we have a lot of samples and I select a complex enough model, then this can be trained, can get the information from the samples and be trained on those. Still, there is a need for tuning, and if somebody is, let's say, decides to do tuning for a big model, the same process still holds. Of course, it depends on the problem. If I have a very big model, perhaps it is better to follow another strategy for the parallelization, to distribute the models on many GPUs. It depends. But usually it is not the most significant thing. This is very useful for small datasets with a lot of noise. If I have small datasets with a lot of noise, then the parameters of the model affects vastly the accuracy. I mean, like 10 or 20% if I select the wrong parameters, which is also very, very common in industrial or real-world datasets from medicine, from business, etc. Yes, thanks, Marios, for the clarification. Yes. Okay. So I continue now with the second part, how we distribute the model across threads. If you remember this figure here, I said that I will send one model to each thread. The first thread will train this model, the second this, etc. Or the first two threads this model, because I want to exploit optimally the power of the machine. How we do this? We use the multiprocessing library of Python. Personally, I tried a lot of things. I found this approach quite useful in practice. This is the method for the multiprocessing. The idea is very simple. The first 4 lines are some dictionaries but distributed these dictionaries where I will store the results of each model. And then for iteratively for the number of combinations of the tuning parameters, as I presented before, I start a new process P, which is a multiprocessing.process. And this command here puts the process to a queue in order to start when some threads are available. This process has some parameters. The first is a method for the training. The method is train XGB false. I will present the method afterwards. And this method has many parameters. One significant parameter is the blast threads. I will present in the following way. Okay, so this loop is for distributing the processes to many threads. Then finally, here I have a same for loop, but with only one command, the proc.join. Here I join all the processes, all the results. I wait each process to stop, and I gather all the results. One note is that the results are gathered in these dictionaries, okay? we have a dictionary for the training accuracy, another for the validation, for the test, and this is for the best number of rounds for XGBoost or for epochs for deep learning. I think I will present it from the code now. Just here. I mean, this function training, I have this method for that I presented before, and this is the method for training the false. Okay, first we have we select a classifier or a regression or a regressor for XGBoost. We define the number of estimators, the number of trees that I will use. Okay, the important part is here in these lines. I will increase also the font. Okay. What I do here, for each fold in the number or in the range of the number of folds, I call this function here, the excuse me, this statement with thread pool limits with user API blast train the XGBoost model. Why I do this? I go back to the slides. Here is the reason. Some parts of the code use the very well-known library NumPy. And this part of the code, the XGBoost part, excuse me, NumPy uses a particular OpenMP implementation, specifically libIOMP5. XGBoost has another OpenMP implementation, libGOMP. Having two different OpenMP runtimes in the same code lead to a crash, actually. We cannot have two different OpenMP runtimes. And of course, we cannot change. One idea is to change the code of XGBoost or NumPy, but okay, that would be really hard. So how we solve this? We use this package. This is a really useful. Personally, I found this really useful package, the thread pool CTL package that is capable of using different OpenMP runtimes. This is not only the only reason because we use this package. There is another one. Because as I said, I don't know a priori how many threads I will give to each model. Perhaps this is a bit confusing, I know, but the idea is here. Let's say I have 256 threads. One thread is for running Python, so I have 255. And I want to train 1,000 models. Okay, then the multiprocessing library will distribute these models. The first will start training, the second will start training, etc. When the first 255 will have already been trained, it will start again automatically. And this is okay. But especially in the final round, in the second round of the tuning process, if I have 50 models to train and 255 threads, then I want each model to have 5 threads. However, when I send the job to the Slurm, I start with OpenMP. I export the OpenMP threads to be one. So by using this package, I can also vary. What I'm trying to say is this: that by using this package, I can also vary the number of threads used in its phase, in its round of the tuning process. Okay, two things to remember is that as I said, I export the OpenMP num threads equals 1, and the total number of distributed threads should not exceed the CPU count if this plus threads here is greater than 1. I say again, the idea is to do multiprocessing for the tuning. I split the models to many threads and then I wait each model to finish training. But because I had this problem with the multiple OpenMP runtimes, and also I want each model to have a specified number of threads, I use this thread pool limits library. Okay, let's continue with some results. This is a data set, a really tall data set with 100,000 samples and a few variables, like, if I remember well, 10 variables. Okay, we have 255 available threads. Now, if I run 1,000 models, let's say that I start with 1,000 models. Okay, here in the plot, the bar plot, I have the average compute time for 100 models, for 1,000 models, and for 10,000 models. Okay, so when I run 10,000 models, I expect not to have 45 times 10. If I want to think a bit around this fact, because I split 100, let's say I have 100 models. I give one thread per model, but I have 255 threads. So the 155 threads are sleeping, are not utilized. So actually, when I run for 1,000 models, then I expect the compute time to be 4 times the compute time of the 100 models. And approximately, of course, because we can never be accurate here, this is 4 times 45 is 180. It is close to 140. And of course, is far from 450. This is a numerical evidence. Of course, we can see this using htop command. I can present it later interactively. But okay, we can verify that the parallelization worked here. Similarly, if I train for 10,000 models now, which is really heavy, okay, I expect the time of the 10,000 models to be 10 times the 45. Yeah. Okay, so it is sorry. Yes, 100 times 45 would be 4,500, which is far bigger than 1,100, which is the actual time. So this is another numerical evidence that the parallelization works. Similar results for the second rounds, okay, which has the second round has more epochs and fewer models. If we do the calculations, we will obtain the same image. Now, regarding the final blast threads, because as we said, we have 2 rounds for the tuning and 2 rounds for the tuning and 1 final round where I train the final model with all samples. And I scale here the number of blast threads used to train this model. We can see that the scaling after the 8 threads is useless. So this is another evidence that, first of all, the process is useful and that we do not need to use more than 8 threads. Okay, some results here regarding scaling. Now, I have 2 different data sets. The first is the Steel SSI with 98,000 models and 6 features. And I ran this using 256 threads and then using 8 threads, which is similar to a personal computer. Okay, for the first, sorry, I also use 100 rounds in the first part of the tuning. And 1,000 rounds in the second part of the tuning. Except the modeling star where I use these numbers here. Now, we can see that we have a scaling of 33 in the first tune, of 6 in the second tune, of 9 in total. We have 10 times faster or 33 times faster in the first tune. And similarly for the other data set, the scale factors are 22, 9, 13, 27, 42, 37. So, some conclusions, because I hope I did not confuse you a lot. By following this parallelization strategy, we have, and using only 1 single node, we can have a scaling of times 20 or more. It is one important part was the optimal number of rounds. Okay, we have to keep track of all the possible rounds during tuning. The second, the third was the 2-step tuning process. We use 2 steps for the tuning. And of course, I have to say, as this is a EuroCC event, if you do cloud computing for all these calculations, the scaling is, let's say, infinite. Okay, that's all from my side. We can discuss or can ask questions. And then I will present very briefly how we can send this job on a supercomputer, and we can close afterwards. But first of all, please let me know of any questions, things that are not clear, etc.
If there's any questions from Nikos, raise your hands on Zoom. Otherwise, he can continue. Go ahead, Nico. Okay.
Okay, I will now send the job to, I am connected on Meluxina. I use remote Visual Studio Code. So I can have my code and the terminal as well on the same environment. I have prepared this batch script. I load some modules. I export the number of threads, and I call this Python. This is the main Python script, the nbml.py. I use here the parameters of the model. I define the parameters of the model, and everything is performed with this function. We have the selection of the tuning parameters, the combinations, and then we call the run multiprocessing deep NN, which is the method I presented. And then for the first tune, here I select with ArcSort the best models, and I run the same method again to train the best models. And finally, I select the final best. Okay, so I have this batch script. I will send the job now. It is sbatch svcpu.sh. The job is submitted. Okay, I will SSH to the node allocated for my job. And with htop, I can monitor the utilization of the threads. Here I can see that I have a new slurm.out file with the results. Still, it is reading the dataset because it takes some time to read the dataset, and I do some, I call some functions for cleaning the dataset. So it will take some time to start training. Here in the slurm.out. Meanwhile, I will say that similar is for XGBoost. And here we can see that we already have 250 threads running, and probably we will, and we already obtained the first results. Okay, each line here is a different model. This has already been trained, and I have a training accuracy, a validation accuracy, and a testing accuracy. How many models I train? I train 1,000 different deep learning architectures here, with 100 epochs each. Okay, so, and in the second round, sorry. Yes, in the second round, I have 1,000 epochs, and 10 models. Yes, in the first round, I have 250 models with 100 epochs each. I selected this to be almost identical with the number of threads. Then I have 1,000 epochs and only 10 models. So in the second round, I will have multiprocessing. Okay, multi-threading with OpenMP. For the deep learning part, I will have 25 threads per model because I have only 10 models. As you can see, some of them have already finished. That's why I have only 75 now running. Okay, and I have all the results here. It is still running. It will take some time because now I have 1,000 epochs, but okay, it is really faster than a laptop. I mean, okay, training so many different models. Okay, I will stop this now, and I will run the same for XGBoost, which will be even faster. I will comment this part and I uncomment this. Here I have in the first round 10,000 models, 10,000 models and 100 rounds. And for the second part, 10,000 rounds and 100 models. And the final blast threads are 5. Okay, so I again call my batch script. Okay, it is already allocated. I SSH to the node, and I monitor with HTOP. It takes a couple of seconds to start to read the data set, clean the data, etc. I can see everything in the corresponding Slurm script. It is still reading. Okay, and you see that it has started training. Here we have this. I mean, personally, I find this amazing how fast it can train thousands of models. Okay, it is not only the models for the models; it is that we gain in accuracy, in compute time, and also in generalization accuracy. We have here like models. If you see here is the ID of the model, you may notice that these are not in order because of the multiprocessing library. The first model that finishes, then this is its results are printed. So this ID regards the model that finished this particular time. Okay, of course, it's still running. We have even more results here. Okay, we are around the middle, I guess, for 4,000 models. You see that some of the threads are not utilized because apparently the majority of the models have finished training. So we have only some of them running. Okay. Okay, this will finish and then the second round will start. and we will have the final result. I don't think it's worth to wait. I like just to highlight the efficiency of the algorithm. So that's all from me. Again, if you have something to discuss, or we can close the session. Thank you for your attendance. Thank you, Maria. Thank you too for the questions.